Okay, so we'll get started. Um, Hello, everybody. I am your presenter today. My name is Shay Fagan. I am a team lead here at Vike Labs. I'm team lead of the Degree Planner project and also on the admin team. And today I'll be talking to you about Git and a little bit about GitHub. We're going to be talking about what Git is, how it works behind the scenes, how to use it, all the commands and what they do. I think a lot of people, a lot of people understand or know how to commit and make changes in Git, but they don't really know how it works behind the scenes. And I think that that's one of the reasons why it's really hard to work with Git and, manage your changes and, get out of sticky situations, which happens all the time. It happens to the best of us. I have totally lost tons of data before. So yeah, hopefully this workshop helps clarify some things and that won't happen, or you'll be able to get out of those situations. So let's get started. So who am I? I kind of look like that guy on the right. And some simple facts about me that you won't find on my LinkedIn. Figured I would leave out the fact, all my generic LinkedIn facts, but the things you won't find on my LinkedIn are that I have a dog with no teeth, who is right here. Okay. And I have a Costco card, but I do not own a car, so I'm currently looking for friends with a car who are interested in going to Costco. Yeah, that's pretty much all there is to me. Pretty exciting. So we'll just get started now. Oh, my dog just let out the fattest sigh. Okay, so what is Git? Well, Git is a distributed version control system. What is a version control system? Pretty self-explanatory, I think. It's a software system that tracks changes made to some files. It could be one file, it could be tons of files. It's kind of an abstract or general concept. You could have a non-software version control system for your documents. You could just be duplicating each version and putting them in folders, and that's sort of like a version control system in a way. So. And we'll see that actually is kind of how it started. So what is a distributed version control system? Well, there are three kinds of version control systems. There is a local version control system, which is basically everything exists solely on your computer, files and versions, and it's not built for collaboration. It's not fault tolerant. Because by default, you can back up, but the idea is if your computer crashes or something happens to your hard drive, you lose all your information, which makes sense. That's kind of the same problem with just copy pasting. Local version control systems are still around and used today. So one example is GNU RCS. That is still shipped in a lot of operating systems, and it's kind of used behind the scenes. So the next kind of version control system is a centralized version control system. And this is also pretty common today, although it's kind of waning, and we'll see why in a second. With a centralized version control system, everything exists on a server. So it's kind of like a local version control system, but instead of being just on your computer, it's on a server that, is on a network. So all the files and versions are on this server, and it supports multiple contributors. But in order to use the system and work on the files, you have to connect to the server, check out the files, modify them, then push the changes. So if you want to think of like a non-software specific example of this, you could think of like Google Drive as kind of like a centralized version control system. So, you have some form of version history in Google Drive, and but you don't have it's not on your computer. It's just on their website, and you have to like download the file, edit it, and then you can re-upload it or edit it in their editor if it's supported. So this isn't really fault tolerant by default either. It is if you're using, in the case of Google Drive, it is, because that's not going to go down. But in terms of like other systems, it's not really that fault tolerant, because if you're hosting it yourself on your server and your server goes down, now you've run into the same problem as the local version control system. So the only, silver lining there is that if you might have some potentially outdated copies of files on some of the contributors' computers. So centralized version control systems, bit better, works for collaboration, still not the perfect solution, but there are still centralized VCS platforms around, like Subversion is one. If you've seen SVN, that is a very popular one. It used to be like the version control system for developers, but it's been slowly, I almost want to say rapidly now, decreasing, and now it's been found that Git, it's over 70 or 80% of developers use Git, according to a Stack Overflow survey. So it's still around. Subversion still gets updated, just like the other GNU RCS, that's still updated. Another example would be Perforce, but we're really concerned about the distributed version control system. So that's what Git is. With a distributed version control system, everything exists on a server, all the files, all the versions, and it supports multiple contributors. So what's the difference from a centralized version control system? Well, you can probably tell from the name. Centralized is on one central server. Distributed is also on a server. But the difference here is that all contributors have a copy of the project, including all the files and all the version history. So there's no checking out one file and then having to re-upload it. And it's like, if you lose it, if the server goes down, you're screwed. That doesn't happen because everyone has a copy. It's kind of like, it might be a bit of a reach to compare it to this, but if you think about blockchain, how everybody has a copy or of the blockchain. Now I won't even pretend to really know what I'm talking about with that, but I'm trying to draw some analogies here. You could also, if we want to go with the cloud storage analogy, then OneDrive or Dropbox, if you notice that the files are on your computer and you like drag them into your folder, it's actually a directory on your computer, and then that just syncs with their database. So that's kind of like a distributed VCS. So this is more fault tolerant, assuming multiple people are working on the project and keeping the repos up to date. Then if the server did go down, you'd be okay. Sorry, that water went down the wrong pipe. It's not perfect either, though. Most people don't host a Git server on premises, though. They use something like GitHub, which we'll see later. So we don't really have to worry about the fault-tolerant nature of this. So an example of a distributed version control system, as we mentioned, Git. Another one's Mercurial. So yeah, now that we understand a distributed version control system, as you can see, you've got everything kind of duplicated. We can talk about Git again. So what is Git? Well, as we said, Git is a distributed version control system. There's not much more to it. There's not really that much that's super unique about Git in terms of like distributed version control systems. It's pretty, it's the standard. The other main fact that I really want to emphasize is that Git is not the same thing as GitHub. And we'll touch on this later, but basically Git is the version control system. GitHub is a platform that supports Git. It allows you to host Git repositories on it, and it has collaborative tools, but they are not the same thing. So, so we'll talk more. That difference will become more apparent as we go on in this workshop. So I've used a couple terms already. The first one being repository. Now this is a really a core concept in Git. So what is a repository? Well, a repository is just a collection of files and folders with revision history. All file formats are supported. I actually know people who use Git for their like documents. Like they write resume1 rather than writing like resume1.docx, resume2.docx. They actually use version control for it, and it works great. Keeping in mind all file formats are supported, but Git is optimized for text-based file formats. So pictures not as great. Still works, but it's not going to be as effective. Just the way the diffs work and how it calculates differences between files, which we'll talk about as well later. It's not just code, but for the remainder of this workshop, I will be referring to the project files and subdirectories as the code base, when it could be in fact just a repository of plain text files. But just to avoid confusion, we'll assume it's code for this workshop. So a repository is also, it's a local database that stores versions of the files. As we saw in that diagram, it's on your computer. Now it could be on a remote as well, which we'll talk about as well. But without somewhere hosting it, Git is almost kind of like a local version control system. If you're not hosting it anywhere or making the repository publicly available, it is on your local computer. But you can also track publicly hosted repositories, and that's where that whole mirroring comes in. So we'll see that one option for that is GitHub. So we're going to start with a small activity. So I'm going to do it on my screen. So if you don't have, you're not on your computer, you don't have a shell ready to go or whatever, you just want to follow along, fine. But I encourage you, if you do have the prerequisites completed, and those prereqs were that you have Git installed, you have a shell like, command prompt or terminal or bash or Z shell or something like that, then you should follow it. You should try and do this because it'll all these kind of activities sort of build on each other. So it'll be, if you miss one, it'll make it harder to do the other ones. So so we'll get started with this one. I will show my shell in the side here. Everybody can see my shell. So first thing we're going to do is we're going to initialize a new repository. So with that, all we have to do is git init. And if we're in a folder, like if we already have a folder that we want to make a Git repository, then you would just change into that directory and then do git init. But if you want to make a new folder, you would do git init and then let's say git workshop. So that created a folder called Git Workshop, and it also created a .git folder. So if we do ll, which is just an alias for ls-l, we can see, oh, that's weird. Okay, it looks like it's not showing up on mine, but it is there. We can do ll.git and we can see the folder there. So let's talk about what's in that. Oh yeah, I think it depends on what shell you're on. Somebody's telling me ls-la. Yeah, normally it depends on what shell, but normally like on my other shell, ll, which is just again an alias, is set up to do ls-la. So it worked on my other shell. But yeah, if we want to do with ls, you can do it that way. That's right. So thank you for that. So if we go into our .git folder and we do ls-la, we can see that there's a few folders and files in here. So let's talk about what those are. So head, the first thing here, which is not initialized yet, is a reference to the most recent commit in the active branch. So a few terms in there we haven't covered yet, but that'll make sense soon. Basically, if we think of this whole file history as a linked list, that's the head of the list. And that's exactly what it is. It is a linked list. So what is config? Config is your repository settings. So I would actually encourage you, if you've still got your shell open, to do to set up your config. You can do git config user.name. I think it's equals. No, it might be this. Yeah, and then you can do git config user.email. And this will allow you to, when you commit to a repository, it'll track your name and an email. So this is also important for when you're using a GitHub repository. You want that email to match what your GitHub account is, but more on that later. Description is another file in there we can see here. You can ignore that. It's not really used. It's used by GitWeb, which is a Git interface. That's also, it's not really used. So we can just ignore this. It's not really what you think it is. Hooks is interesting. That's a folder that contains scripts to be executed at various times through the Git flow. So you can have pre-commit, post-commit, things like that, pre-push, post-push, all that. So you could have like a linter run or something like that. Info is all your additional repository information. One key thing in here that I feel like most people don't really know about is that we can get we'll talk about this a little more in a bit here, but the way Git tracks your files, we can also say we want to ignore certain files. Say we have some private API key that we don't want to push to our repository. We might ignore that file, but maybe we have like a file that is in every one of our repositories for whatever reason, and we always want to ignore it. We can do that in that info folder. There's a global exclude list. So that's like a global.git ignore if you're familiar with that file. Objects is really interesting, and we're going to dive into this one a little bit later. Objects contains all our Git objects. This is basically everything. And refs. Refs and objects contains everything pretty much that Git needs and uses. So refs is all the references. So this is branches, tags, aliases, things like that. So most of these files will be empty, or they don't really have anything interesting in them yet. But we'll see as we go on through these activities that this starts to get populated and things start to appear in there. So what is Git history? Well, Git history internally, it's a linked list. If you've taken, I think it's 111 CSC 111 or 115, you might have learned about linked lists. I'm sure everybody loves pointers. That's at the core of this as well. So Git, I want to draw an analogy here. Git is kind of like a timeline management utility. So history is recorded as discrete points on a timeline, and each one of these points is a snapshot of the code base. So what is a commit? I've mentioned that word. Those points are commits. Those snapshots are commits. And this is an important differentiation here. The wording here is very important. A commit is a snapshot of the code base at some point in time, not a diff. It is not, something like Subversion, which is a central VCS, uses diffs, so it only tracks the differences between each file iteration. Git actually takes a full snapshot of the repository each time you commit. And we'll see it optimizes that through compression, but this is generally why you shouldn't track really large files in your Git repository. You shouldn't have like terabytes of stuff in a Git repository. That won't work well. The advantage of snapshots over diffs is you can switch to a specific commit and it's instant. There's no it doesn't need to calculate, it doesn't need to generate the file based on all of the diffs and add them all together to create the actual version of the file. But this is important because it is pretty efficient, and it doesn't track files that it doesn't snapshot files that haven't changed. And we'll see that a little bit later. But it does take a full snapshot of any file that's changed. So even if it's one line, the whole file is re-snapshotted, if you will. So there's a few stages before we commit a file. Files go through these stages, and this is going to be a little confusing, but we'll dive into each stage in a second here. So untracked is basically these are files that are not tracked are ignored by Git. Tracked means that they are monitored by Git. So we start every file as untracked. If we create a file in our repository, it's untracked. Sorry, I'm going to jump back into this one here. If we create a file in our repository, it is untracked, and then we can add the file and it becomes staged. Goes right from untracked to staged. Then if we commit that file, goes to unmodified, and that's how Git knows it's tracking it but hasn't changed. So if we make a new commit and a file is unmodified, it will just be the reference will stay the same. There's no it won't recreate the file. If we edit it though, it becomes modified, and then but it's still tracked, but we have to stage it before we can commit. So this is a little confusing. I know that was a lot. So hopefully this next slide will make it a little more sensical. Files can be untracked or tracked. So untracked files are ignored by Git. They are not in the last snapshot, and they are not in staging. So, and tracked files, on the other hand, are monitored by Git or tracked. So unmodified files that are tracked have not changed since the last snapshot. Modified files have some difference from the last snapshot that Git recognizes. And if we want to commit modified files, if we want to push those changes, we need to stage them. So staging is the environment, or the kind of index, and we'll see that's actually what it's called, is the index, is the group of files that are modified and are ready to be committed. So and then there's stashed files, which is not really, it's not like it's not a third type of file. I just kind of threw it in here because it kind of goes along with it. It's the second thing or another thing you can do. You can stash your files. So if you're working on some changes and then you want to check out a new branch, or you want to do something different, but you want to like save your changes and have them be reverted, most people would probably, including myself, I do this a lot. You copy the whole file to like just a plain text file and just have it like a scratch file. But stashing is a way to basically save everything in staging into a stash. You're putting it into like a little box and that you can take later. So it's like duplicating a file and then reverting it to the original state before you started working on it. So we've covered a bit of the life cycle. Hopefully this slide makes a little more sense now. But moving on, git undo. This is something that everyone wants to know. Sorry, doesn't exist. There's no git undo command, and it's not as straightforward as you might hope. Undoing there's various ways, and we'll see later that undoing is really a misnomer. You don't really undo anything in Git. You can like travel back in time, but there's no undo. You can just travel to a point where that change didn't exist. So, but talking about commits, these are easy commands that'll come in handy. If you want to edit a commit, like maybe you committed the wrong thing and it's just the last commit you made, you just do git commit -- amend, and it'll replace the last commit with all the files in staging. So if you have like a new file in staging, your whole commit will be replaced with just that file. If you don't have any files in staging, then the commit will be left as is, and then also you get an opportunity to change the commit message. So if you've committed before that, like maybe you made one commit and then you made another one and you realize the first one you made was like the wrong thing, that's a bit trickier, and we'll touch on that later. That involves traveling to another point. It's not as simple as just reverting the last commit or amending the last commit. To unstage a file, you use that restore command. Same thing to revert an unstaged modified file. Be really careful with that last command because that literally deletes the changes from your computer. So we're going to do another activity real quick. This one is going to be a little bit more involved. I really encourage you guys to do it and follow along with me if you'd like. So we're going to make some changes. Oops, sorry about that. We're going to make some changes here. So I want everybody to, in their new repository that they've initialized, I want everybody to create one file called hello.txt. So this is, you can just do hello world, echo hello world, and then hello.txt. And if we do git status, we can see that this is an untracked file. It's not in staging, but Git recognizes there's something there that it's not tracking. So we can leave that. We can have that file. If we change it, nothing happens. But if we want to commit it, so in that case, we're going to add the file. And you can also use file matchers, so you don't have to do that hello.txt. You can also do dot, which would do everything in the current directory or further in. You can do star.txt if you want to do all the text files. There's matchers. So let's just do dot. That's the most common one. It'll do your entire area. So now if we do git status, we can see that the file is now in staging. So if we go back to this diagram, few back, we added the file and it's in the staging environment, and that's it. Now we want to commit it and it's going to go back into the modified stage. So if we commit it, we do git commit -m, and let's make our commit message we want to make commit messages. That's something that's really important, especially when you're working collaboratively, because you're oftentimes going to go back and you're going to look at your commits and you're going to try and reason about them. So you really want to make sure that commits are descriptive, concise, and you're very clear on what you were doing. And also, not the commit message, that is important too, very important, but also what you actually commit. So as a rule of thumb, commits should be all related. Like everything in one commit should be related. It should be one logical piece of work. So a feature, if you're adding a feature let's say you have a to-do list, you're building a to-do list, you want to do add to do item would be a commit. You wouldn't want to do like adding and removing to do items, because you might, I mean, you could if it's a small amount of code, but you really want to keep them logically organized so that you can go back and read the commit and see just what was changed. And it's very easy to reason about. And that's going to be why that's important will become clear when we introduce the concept of pull requests and collaborating on GitHub. So next step, we want to commit this add hello.txt, or let's say add test file to root directory. So that tells us some information about it. This is the object ID, which we'll talk about a little bit later. This is just a message that tells you it's the root commit. This tells you exactly what happened. We inserted one line in one file, and it was a created file. So the create mode is here, the file name's here, and we can go ahead and move on. So if we do git status, nothing, everything's fine. That means that that file is in unmodified state. It's tracked and unmodified. So now we can do our second commit. We want to create a directory called foo. And Git actually won't track, you can't track a directory that's empty. And won't get into why, it's not really important. But the point is that if you add directories, they will never be tracked unless there's a file inside of it. So we're going to add a file. So let's do echo blah, 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 and we'll call it flimflam. We'll make it in the foo directory. And flimflam is one of my favorite words. It basically means nonsense. So now we can see we have just the one directory, and we have the file in our root directory. If we go into foo, we have flimflam. So now if we do git status, we can see we have the directory, and it doesn't show you what the file is. If we actually add it, it will tell us what the file is. But we have a few more things we want to add first. So let's do make directory foo bar. And then we're going to also make one more file called baz. We're going to say foo bar baz. So now we have git status. We basically just have the foo directory because everything we've done is in there. As soon as we add it, though, we will see all of the files that we added as well. And the directory is not really there. It's the files that are tracked. So now we can do our commit. And let's call it add some nonsensical. Tells us that there were 2 insertions and 2 files created, and it gives us that commit ID again. So now we have nothing in our commit history, or sorry, nothing in staging. We can move on to the third commit. And this one I wanted to edit baz, and we're gonna change the wording or the contents of that file. So let's do vim foo bar baz.txt, and we're gonna change this to baz bar foo. Same seems reasonable. And if you're using Vim, I did advertise that I'll teach you how to quit Vim. I'm not gonna pretend like I'm a power user with Vim. It's an extremely intimidating tool to use. I do know how to use it, but I don't use it regularly. I don't think it's necessary to use regularly, but you will have situations where you will probably use it. And quitting Vim seems to be the #1 question that people have because it's not intuitive at all. So to insert anything in Vim, when we get into this state, you press I and see at the bottom there it says insert. That's insert mode. We can escape to get out of that mode. So Vim's like a finite state machine. You have the different states you're in. That insert is really the only one you need to know. Insert, escape to get out of it. And if you're not in a state, you can do colon, and then you can do, if you do Q, it just quits. But if there's changes, then it'll say you can't quit. You can override that with an exclamation point, but the one we're concerned about is WQ. So that means write and quit. Cool. So you can also do that in a text editor if you couldn't figure it out, just Control C out of it and it's all good. So now we can see we have a change. We're also going to do one more change. We're going to move Git doesn't track moves by default. We have to do it with their command. again, doesn't really matter why. It's kind of has to do with the internals of Git, which we'll talk about later. So let's move a file. We're going to move foo flimflam to just the root directory of our repository. So now we can say we renamed, and that's basically what we did. I mean, we moved it, but that's kind of the same thing. And that's already staged. We have to add the other file, though. Now we can commit. We'll do edit some files. So now we have our 3 commits. And hopefully everybody's up to speed here. That's basically it. And we'll move on to the next part here. I wanted to touch on one thing as well, though. The reason we can commit, or we can amend the last commit and not, so I mentioned in the previous slide, you can amend a commit, and I did list the command there on this slide. The reason we can only amend the last commit was because there's no other commits pointing to it. It's at the end of the list, the linked list. So changing a commit completely changes its commit ID, its object ID that other commits point to, because that ID is actually just a SHA-1 hash of its contents. So if there was a child commit and we amended the commit, it would have to change the child commit as well. So that's why amending a commit, it only works for just the last one, because there's nothing else pointing to it. So moving along, we're going to talk about traversing history. So we know that we have these little points on this timeline called commits. We also have this pointer that we mentioned at the beginning, head. And now we can see what that does. If we have 3, there's 6 commits or 7 commits here. But if we see, let's say we have our 3 commits. This was the first one we did, second one we did, third one we did. Head would be pointing right here. So let's say we've done 7 commits. Head is pointing right here. Now, we can move head. We can move through the timeline. No problem. Oh, I did the animations here wrong. But basically, if we visit a non-current point on the timeline, so if we move the head pointer from here to here, we will lose, we will be in a detached head state. So what that means is basically if we make any commits in that state, they will be detached. There's no associated branch. We can still visit detached commits, but only if you know the object ID. But it can almost always be recovered. So you're not going to lose data. As a rule of thumb, if something is committed and you lose the commit somehow, it's almost always recoverable. But if you have not committed, it's probably gone. I'm sorry. So committing, the important thing with Git is commit early and commit often. I would not apply that advice to other things in your life like relationships. Take your time in those regards. But with Git, you want to commit early and often. So moving on, we can move from commit to commit, but what if we actually want to move like permanently? We want to reset to another commit, basically undoing. So when we move to a different commit, not just visiting, we're actually moving to another commit, we lose all of the descendant commits because we've moved our head pointer and now all these commits are broken off. So they still exist, but they're not going to be pointed to. It's not in our timeline anymore. So they're kind of detached, which is okay. We can still recover them, but we want to make sure we're careful when we're moving commits. So there's two ways to move across the timeline. You can reset with a soft reset, which all changes that basically in this case, all these 3 commits, all the changes that would be in those commits will move into staging if you do a soft reset to this commit. If you do a hard reset, all these changes disappear. The commits are still there, hanging around somewhere, but all the changes are gone. So it's a little harder to access, and it's not like you can just recommit. So this, in a way, you can use a soft reset to undo, and you'll have a chance to modify the commits. And there's other ways that we'll touch on as well. So Git has this internal data model. We know it's a linked list for commits, but each object in this linked list, a repository is really just a key value store. Each object is referenced by its object ID, whiwhich is just a SHA-1 hash of its contents, as I mentioned. And and these are all linked together in some way. So there's three kinds of files. There's blobs, which are the most granular. There's trees, and there's commits. Blobs are files, trees are directories, commits are snapshots. That's the simplest way to remember it. But what does Git history actually look like? Well, we can see in this image here, this super well done image that I made in draw.io, commits basically point, if this is our head commit, there's nothing pointing to it. I didn't include the head pointer, but it would be pointing right here. This is its parent. This is its parent. Each of these commits has a root tree. So in this case, the root tree would be our directory, like our root directory of our project. And then that would have some trees and blobs and all sorts of things corresponding to files and directories. So let's say in this first commit, we have our tree, our root tree, and we're introducing a directory with 2 files in it and a file in the root directory. These are all, that means that this root tree is going to change. These are going to be changed. I mean, they're being added, so they're changing. And this is going to change. So that's why they're all white. Let's say in the second commit, all we're doing is adding a tree to the root directory, a new directory with a file. So we're not touching any of the other stuff. We're just adding this part. You can see this mimics this part. That means that this stuff didn't change. The only thing that changed is this root directory, because it now has a new listing, which is a subdirectory with a file in it. And if we notice, when I said a snapshot of the whole repository, the commit does contain a snapshot of everything. Even though these didn't change, still takes a snapshot of them. But the thing is that the reference is the same. So these objects have IDs that we can reference to them, that we can use to reference to them, and those IDs did not change. So in this tree that has blob file name pairs, tree directory name pairs, it's pointing to the same thing. This tree here is pointing, this is equivalent to this. It's pointing to the same tree. So it does duplicate it in the commit. It lists it again in the tree, but it's the same reference. So nothing changed. And that's why it's efficient. We're not changing. If we didn't change the file, we don't need to take a new snapshot of it. But these ones are, these ones on the right. So we can see here's another example. We just modified this, we add one file in the root directory. We modify it. We already had it. This changes. The root directory would actually also change. I think I might have accidentally colored that in. But yeah, so that's how it works. Blobs literally just have binary content of the file. Trees, the directories, have blob file name pairs. So like the ID and the file name. And then they also have tree and directory name pairs. So that's like more subdirectories. Commits are the interesting one. They have the root tree object ID, so that would be this ID, the ID of this tree here. The author and committer, which is what we were doing earlier with git config. And then it also has the commit message. So this diagram shows where everything is stored in Git. So we have these commits here and these trees, and this is all stored in objects. And then we might have a branch, which we'll talk about later. These are the references. And then the index and head. The head points at the tip of the branch, which is, we'll talk about later, but a branch is just a reference to a commit. And the index is our staging environment. So we're going to do another activity. I realize now that I kept my shell on for the past few slides, but that's okay. Hopefully it's still, everybody's able to still see everything. So we're going to do an activity here. I would encourage you to do it on your own, but we're not actually going to be committing anything. So if you don't do this part, you're not going to be like at a loss as long as you do follow along. But I encourage you to do it on your own if you want to. So we're going to examine the objects involved in our first commit. So let's do git log, and git log shows us the last X number of commits. If we do git log one line and graph, we can get a shorthand version that's a little prettier. So if we take a look at this ID here, and the ID is actually much longer, but it abridges it or truncates it to a point where it's unique, still unique, but it's short enough that you can easily remember it, or not remember it, but write it out. So let's do git cat file. Git has if we actually cat, we can actually go, if we do ls-la and we do .git/objects, and then we find our object. So if we look at the first 2 digits of our thing, it's AF. So we can go to Oh, that's not even in there. Oh, no, it is at the bottom there. AF, that has the one thing. So if we cat that, it's a bunch of garbage because it's a binary file. So Git has a command that we can actually do that and see what it actually is. -p just means pretty. So if we do and now we don't have to do the whole path. We can just do the first, we can just do this ID here. Oops, sorry about that. And then paste. Cool. And we can see exactly what's in that commit. So it's wrapped here. That's why the zero's on the other side here. I'm just going to zoom it out a little bit. Cool. So in this commit, we can see that the tree is there. This is the object ID of the root tree. So this is our root directory of our project. This is the parent commit. So we are actually looking at our third commit. That was my bad. I said first, but we're looking at the third commit. We can see this is the parent commit. This is the author, this is the committer, and this is the message. So let's actually go back. Let's look at the first commit. Okay. So we can see the root tree is there, but there's no parent because it's the root commit. So let's look at that tree. And we can actually also just do git ls tree, and then we can just see the tree. So and it doesn't have to be an exact tree, so we can just say the commit ID, and that'll work. It'll recognize that that's the oh, we actually did copy it, so this will be fine. So we can see in this tree, all there is one listing, because that's all we have in this point in the commit. All we did in that first commit was added one file, and that's what it is. We've got the blob here. It lists the file mode. It lists the type of the object ID, and the name. So really, this is what I was mentioning here. This is the SHA-1 hash and the name of the file, because we don't care. The name of the file is not stored with the file, which is consistent with file systems on your operating system. So we've looked at this tree. Now, what about that blob? Well, if we do git cat file 980A, we can just say like maybe the first 6 digits of the or characters of the code is fine. That's 7, but we can see that's all that's in there. That's the only thing in the blob is just hello world. And if we cat it, it'll be binary. It'll look a little weird. So we use cat file, but that's pretty neat, right? So if we now look at our git log again, and we do, okay, let's look at the second one. So this is the second one, the root tree directory. If you notice here, it changed. And that's what I was saying, right? Our second commit, we changed what was in the root directory. So the hash of the root directory changed. So that's why we have a new ID. This parent is our first commit that we made. So let's look in this tree and see what's in there. So as a reminder, we'll look at, this is in our first commit, what the tree looked like. Again, I'll zoom out a little bit here. That's what the tree looked like. So now if we do our second commit right here, now we've got another tree. This is our first commit when we made foo, and we've still got the same file. We didn't touch hello.txt in the second commit. So what I was saying about how it uses the same reference, it doesn't re-snapshot it, you can see this ID here is the exact same as the one here. Even though it's a new commit, it uses the same ID because it doesn't need to recreate the file. It keeps that version consistent, but it does include it in the snapshot. Just a reference though. So it uses the same reference as before. So let's dive into here. We can actually do ls. We don't have to keep going in every tree. We can actually just do git ls tree -r, and it'll go into each subdirectory. So if we do the same ID, we can see that we have, oh, actually I did the ID here. Let's do this one. So let's do git ls tree -r, and then we've got, we can see this is basically our entire root directory with all the subdirectories. We've got our hello, which again, the ID has not changed. And we also have foo, the directory foo. and then in there is flimflam. So if we actually did without the, so if we look at before when we didn't do the -r and we just did that, we can see foo, the object ID of the directory is not in here because now we're just visiting each tree. So this is equivalent to, this is like going into each tree. It's recursively visiting each one. So we've seen enough. It's really okay. That's okay. We can do any of these files and it'll look the same. Exactly what we expect. We can do the directory foo. We can do the file flimflam. Blah, blah, blah. Exactly what we expect and what we talked about. We can also use some handy little tricks to do this. So we can actually do git cat file head, and head is our latest commit. So this is the third commit now we're looking at, right? So this was our last one. We did edit some files. We can also look at the tree really easily by going like this. Pretty neat. So we never changed hello, so the ID is still the same. If we look here, foo, we did change, so the ID has changed, and flimflam is moved, but the ID didn't change, right? Because we just moved it. So if you look at in here, when we visited before, it was in the second commit, it was in the foo directory. This was the ID. Now it's in the root directory, but the ID has not changed. We just moved it. So Git does know when you move a file, you have to do git move, but it knows, and it doesn't create the file or anything like that. So it's pretty efficient. So we've looked at enough. I encourage you to mess around in there, cat file, use the different little helpful tips with the, you can also do head like this, and then you can say that would be like, head is the most recent commit. This would be the commit before that. This would be the commit before that. You can do it's kind of like a minus, but it's a squiggle. All sorts of things. So yeah, we can do this is our first commits tree. Cool. So we'll move on. And I noticed that we are already at 6:57. We did start 10 minutes late. So I just want to say this is 100% going to go over time, but it is going to be recorded. So if you have to go at 7, don't worry about it. The rest of it will be recorded, and we will make sure you get it to you. But I encourage you to stay for the remainder. We'll try and get through this in a reasonable amount of time. I promise it won't be like a whole other hour or even a half hour. We'll try and get it through it in, maybe an extra 10, 15 minutes. But yeah, so this is a pretty cool activity. We can come back to this. You can do this on your own time, but I encourage you to really dig into the commits when you're making them. Like, check out what's inside and look at each object. Look at how the IDs don't change if the file doesn't change. Look at how the IDs do change based on what you do. And it's really interesting to me. And how they're stored. All of these objects, again, as we saw, are actually just stored in .git/objects. And it indexes them by the first 2 characters. So 9.8, this file hello, would be in here. And then we could find the file in there. So we'll move on. We don't need to look into that. So this next topic is really the bread and butter of working collaboratively with Git, and that's branching. So we've established this analogy that Git is kind of like a timeline management utility, right? History is recorded as discrete points on the timeline. We call those commits. Well, we can actually maintain multiple timelines through branching. And if any of you have seen DC or any DC shows, you know that this is obviously not possible after Crisis on Infinite Earths. There's only one timeline now. But point is that we can maintain multiple timelines, and you can see in this picture that we're gonna cover this later, but you can branch off and then you can merge them back in, and this allows us to work in alternate timelines, not even caring about what's in the other one. So now we can all work in our separate timelines, and then we can merge them together when we're ready. It's like you can delegate work more easily and collaborate more easily. You can also just do this if you're doing a solo Git project. It's still helpful to branch, because you might not want to, you might be messing around, and it's easier to mess around in a branch that's not like the main branch. And we'll talk about that as well. So branches are just references to a commit. That's all they are. They're not more complicated than that. I thought they'd be more complicated before I started, doing research on this, but nothing to it. It's just a reference to a commit. They're stored in Git refs heads/branch. So we will, in the next activity, we'll dive a little bit into that. But the idea here is that, yeah, it's simply a file that contains the ID of the commit. That's it. Creating a branch means branching off of another branch. So as you can see in this picture here, we're branching off. It's diverging, right? And if the branch, we haven't made any commits, the yellow branch would still be here. But as soon as we make it a commit, it's in a new timeline. So committing in a branch means diverging from the branch that it is based on. So your first branch will always be main or master. So I want to touch on this really quickly. Historically, the branch was called, it actually started with trunk. That was actually what it was originally called, the trunk. But historically with Git, it's been called master for a really long time. The first branch that's created, the default branch, the one that is deployed in production and everything, that's master. Now, obviously this has, it's 2021. This has some racial connotations to it, and I won't get into it. It's not important, but recently Git and GitHub made a decision. It's not really, it's open source, but or Git is, but the community and the people behind Git decided that this was an insensitive choice of words, and they've changed the name to main. The thing is, though, is that this did just happen, it's maybe a few months ago. It's still happening. People are still transitioning. So throughout the rest of the workshop, I'll be saying main, I'll be saying master. It's just, that's been the way it's been. And the reason I still say master, even though it's not technically politically correct, maybe, is because Git repos by default still create master as the main branch. You can customize. You'll notice that mine is called main, and that's because when I installed Git, I checked a box that said use main as the branch, and eventually this will become the default. But for now, I'm going to still call it master because some of you might not have checked that box and have no idea what main is, because master is the default branch still, and it has been for a long time. So that's the reason I say main/master. Now, the first branch you create will be based off main. Again, I'm going to say main and master interchangeably, so just keep that in mind. You can switch between branches, and the value of that head pointer in the root directory will change to match whatever is in Git refs heads branch. So it'll point to a new commit. And that's your active branch is just that head file, which is really neat. So this next activity, we're going to, I realize I keep forgetting to change the scene. The shell has just been open this whole time. So again, hopefully everybody can see everything still all right. But this next activity, we're going to be creating a branch, switching to it, which we can do with one command, create a file in the root directory, commit it, and then let's examine the branches. So I'm going to do it right here. So if we can list all the branches we have locally, and that's the only one we have, main. So if we want to create a new branch, we can do git switch. And for anybody who's used Git in the past, it used to be called checkout. You would use checkout to check out a branch. You can still do it that way, but they recently added this. It's not that recent, but they added this command called switch because checkout is used for so many different things, and it was really confusing. So they're kind of just abandoning that command, and now it's going to be switch and restore, because checkout was used in the same way the restore was, but it was also used for switching to branches. So it was really confusing. So git switch, I encourage you to use the new command. -c just means create, and then let's create a new branch called my first branch. So we've switched to this new branch. If we do git status, we can see we're in that branch. Now, if we look at the commit log, we can see this. Look at this. It tells us the head of my first branch. Sorry, our head right now, because we have my first branch checked out, our head is pointing at my first branch. If we switch to main, if we do git switch main, it'll show us that we're pointing towards main. And the reason they're both in the same brackets is because my first branch is based on main. We haven't made any commits. So let's check that branch back out, my first branch. And we'll create a file in the root directory. Let's do echo branch file. Or we'll make the text woohoo branches. And we'll call this branch file.txt. So now we have something untracked. Let's add it. Now, if we want to commit it, we can do git commit -m, create file in separate branch. Now, if we look at git log one line graph, we'll see that there's one more commit that's late, that's even more recent. Now, the thing is that this is not on the same timeline as main. It branched off. So if we actually switch to main and we do the same command, we won't even see this new command or this new commit because main has no knowledge of it. It's not on its timeline. So, but if we're in my first branch, we do have that commit. So that's where this differs here. So if we were to do git cat file, and this is really cool, you can actually just type in the branch name and you can see what it is. And this command right here with the branch, this is equivalent to just catting, using cat to, as I say right here, it's equivalent to just catting it. There's no binary encoding. It looks exactly the same. But we'll use cat file so we don't have to use the whole path. And if we just do main, we can see this is the commit that it's using. We can also do a command I didn't include in here, but it's not really that important. We can do rev parse to see the commit that it's actually referencing to. So this commit right here, you can see, is right here. Makes sense. So now if we switch back to, or actually we can just do from here, we can do git cat file, and we can do test my first branch. We can see that's the other commit that we made. It's a different tree. The parent's the same. You know, the parent is what the other branch is pointing to, but it's separated. So, and if we do cat git refs heads main, again, same thing. Pretty cool. Okay, so that's what a branch is. All it is a pointer to a commit. Now, in the documentation, they say a branch is a pointer, a head is a pointer to the currently active branch. I don't like this wording because, I mean, it's true, but branch is a pointer to a commit. So it's just transitively, head is a pointer to a branch, which is a pointer to a commit. So we can really just say head is a pointer to a commit. Head is a pointer to the latest commit in the currently active branch. Okay, so we have multiple branches here. We saw in this last slide, we've got multiple. We haven't merged them yet, though, so like ignore the right half of this image. How do we merge them? You know, you've made some changes in a branch and you want to merge them. Well, Git enables us to merge two branches with git merge. Wow, I know it's crazy how well named these commands are. So when you merge two branches, let's say we've got this timeline here. So let's say this is my first branch. We've created 3 commits. We haven't actually, but let's say we have. And main, or master in this case, has 2 commits, but it's based on this common base. Let's say we want to merge this back in to make the timeline consistent. Sorry, I'm going to do that. Cool. If we do that, we can do that with git merge, and we'll see that's what happens. So it creates a new commit. This is a very important point. When you merge 2 branches, it creates a new commit. And this commit is a merge commit. It's a special kind of commit that has 2 parents. That's all. That's the only difference. It has 2 parents, and that means that it's a merge commit. If you see a commit with 2 parents, it means it's a merge commit. So this commit just brings everything in from this branch into this one. And then after this point, you can carry on in one timeline. Okay, that's great. So what if you make some changes in this branch and then somebody in master also changed some branches, some code, and they conflict with each other? That's called a merge conflict, and it is a huge pain in the ass to deal with. You will 100% encounter these. I'm not going to get into like too many details about how to fix merge conflicts because it's pretty self-explanatory, and IDs make it really easy. You can compare them. But you will get a merge conflict if you try to merge two branches with conflicting files. So if you edit a file in your branch and I edit the same file in my branch, then we try and merge them, there'll be a conflict. We have to resolve it before we can merge. So you can do the merge commit and just fix the conflict in one commit. So let's say there was a conflict in each of these files. We touched the same file that was happening and being touched here. Sorry, my mouse is over here. Let's say we touched this file A in here, and that was also being edited in here. We merge here. We have to fix the conflicts once. Now, what if there's a different way? What if we wanted to change the base because we want to have the latest changes from master on our branch before we do it, and then that way you also won't have to deal with merge conflicts. Because if it's on the latest master, you won't have any conflicts. Yours is the only one that touches the file. So that's called rebasing. So rebasing is notoriously confusing and complicated, and it can be, but it's not that complicated at its core. You are basically changing the base of the branch. That's all it is. So if we have this timeline or these two timelines, we rebase. Let's say we want to rebase feature onto the tip of master. That's what it'll look like. Now, there's the squiggle because we can continue making commits in master, and they would go along here. That's why it kind of goes down here, because it is two separate timelines. It's just that we haven't made any commits here. So you don't have to rebase onto the tip of the branch. You can also rebase onto a specific commit. Maybe I wanted to rebase onto this commit right here. You can do that. You can just type in the commit ID in the reference. You can also type in a branch for reference, because a branch is just a pointer to a commit. So reference is that's typically a commit. When I say reference, it's almost always a commit. But again, branches are basically commits. So you can type in a lot of things. Git is pretty liberal with what it accepts. So rebasing can be interesting because it can, what if, we edited a file A, again, in these two branches, and then we rebase onto the tip. We're going to have to fix the conflicts that arise. We're not going to get any merge conflicts when we try to merge, but we are going to have to, this file that we edited in these three commits has changed. So if we rebase onto the tip here, we'll have to address those conflicts. And we can do that. That's one of the downsides of rebase, is that if you want to keep your branch up to date on the tip of master, you want to do it often, because if you rebase when there's like 8 commits and they all have conflicts, then when you're rebasing, it basically goes through every commit and it reapplies it on the tip of the latest master. It's just reapplying the commits. So if you have to deal with a conflict, it's going to happen in every single one of those commits. You're going to have to fix the same conflict. So that's where rebasing can be a bit tedious. But the use here is that when you rebase, instead of just merging it back in, when you merge all your branches, never rebase, you're gonna have your Git history is gonna look wild. It's gonna be so hard to follow because there's gonna be all these different branches. Whereas if we do rebasing instead of merging, then it'll keep a linear history. So I won't get too much into that. That's a big controversial subject in the Git community, rebase versus merge. I encourage you to ask, if you're on a project, I encourage you to ask your team lead about what they prefer. So like if you've got a PR open and you want to update from the latest master, some people prefer merging master into your branch. Some people prefer rebasing your branch on the tip of master. And those are two different things. They might accomplish the same end result, sort of, but the things that happen in between are different. And the result is, the end result to your eye, the branches are together, is the same, but behind the scenes, it's not the same. So something to take note of. And I'm going to send out some resources at the end of this talk. And one of them will discuss rebasing versus merging in more detail, because frankly, that could be a whole workshop on its own. So rebasing can also be used to rewrite history. And this sounds crazy. And it can really, you can shoot yourself in the foot when you rewrite history, 100%. Now, also, if you are working with a public branch, like you've got a GitHub repository and you're pushing your work that other people are going to work on, you can't rewrite history, because it's set in stone history. So if other people have cloned the branch or the repository and they have that branch on their local machine, if you rewrite history, it's going to totally mess up their timeline. And it's a nightmare to have to solve those kinds of issues. Now, if it's a branch that only you know about, only you are working on it, you can force push, you can force Git to replace the history with your new rewritten history. And you should only ever do this if you are absolutely sure you know what you're doing. And the only time that I would say force pushing is ever a good idea is in PRs when you want to update, at the end of the PR before you merge, you want to clean up your commits and you want to rebase on the latest master. You might force push so that you don't have a ton of commits in your PR. That's fine. But never force push main or master or anything like that, because that'll mess up everyone's copy of the repository. So we rebase, we can rewrite history with the interactive rebase. So it basically, if we say rebase interactively on head, that's a no-op. That won't do anything because head just points to the tip of our current branch. So if we're rebasing onto the same thing we're on, it doesn't make any sense. But if we do the squiggle again, I think this is a tilde or something. No, something like that. Then we can do N, which basically allows us to rebase back to a certain commit. So if we say head squiggle 1, that's like one commit back, not the most recent one, but the one before that. So, and then when it rebases, it's reapplying every commit. So you have a chance to change each commit that it reapplies. Now, you can do an interactive rebase on your own branch. You can just use head. And this is basically what you would do if you wanted to rewrite history in one branch. You're not like rebasing onto another branch. You're not including any other changes from another branch. You're just changing history of your branch, one branch. You would use some form of head or your own branch you could do. If you want to rebase, you can also do interactive rebase onto another branch. So that allows you to, if you're rebasing onto the latest master and you also want to drop some commits or reorder them, you can do that at the same time. So this next activity we're going to do is we're going to work with some branches. This one's a little bit more involved. So I'm going to be doing it on my screen again. And I encourage you to follow along on your shell. And if you can't get it, don't worry about it. Just try your best and it's all good. I'll be, making this repository public so you can all view the commit history and see how it works. And I haven't actually done this activity, practiced it, so I'm just hoping it works. First thing we're going to do, we're in main. We want to create and switch to a new branch. Let's do that. We're going to make 3 arbitrary commits. So let's do test 1. And you're noticing that I'm actually adding all the files at once, but I'm going to do it in 3 separate commits. You can do this. You can, it's advised when you're working on software to work in chunks. Don't do everything at once and just hope it all works, right? You want to do little chunks and test and write, test. So, but it's inevitable that sometimes you're going to write a bunch of code because it's all dependent on each other. And you don't want to commit it all as one commit because you're going to have this massive commit that changes so many files. And I strongly discourage you from doing that. You can pick and choose. You can divide the commits up. You can do it before you commit, or you can use an interactive rebase to do it after. You could commit them all as one and then do it later, split them. That's kind of a pain in the ass, but I would encourage you to do it at the beginning. So let's say I've got test 2, got test 3, now, if we do git status, we've got all these untracked files. Let's add just the one. Now we've got just that one. That's how we can split up these commits. We can say git commit add test1 file. Still have the other 2 files there, but now we have one more commit. Simple as that. Now we can do the next one. Git add test2. And we can do the same commit, change it to a 2. Now we have a second commit. Now let's do the third one. Cool. So git log, maybe one line. We can see we've got the 3 commits, and its main is here. We're here. Pretty cool. Okay. So now let's switch back to main and commit once. So we'll do echo, and let's actually, I didn't include this in the activity instructions. You don't have to do it, but I'm gonna manually, I'm gonna try to introduce a merge conflict. So I'm gonna do, I'm actually gonna do this way. I'm gonna do, yeah, or we'll do it with the merge. Okay, so we'll do git switch. We're in main. We're gonna create a commit. So let's do echo test 4. test4.txt. No, there's not going to be a merge conflict for this part. So we've got this commit. You can see in the log, it's here. Oh, sorry, we forgot to commit it. Git add, git commit, add test4 file. So it's there. If we do our log, it's right there. Now, if we go back to our other branch, git switch, what's it called? I think it was, what was my branch called? New branch. Cool. If we switch back to new branch, we can see in our log, we don't actually even see that commit. Same reason as before when we didn't see it in main. It's not in that timeline. So, but there's a new branch. So if we try to merge right now, our new branch into main, it'll work because there's no conflicts, but we're not merging the latest changes, right? Or we are, like it'll be there, but we don't have the latest changes. So like maybe something was changed that we want to know about. So you should always be making sure that your branch is up to date with the one it was based off of. And whether you want to do a merge to update your branch or a rebase, that's up to you. And I would discuss it with your team lead because you should have a consistent system. So let's do a rebase onto the, we're going to do a rebase in this case. Let's do a rebase onto the latest main. So git rebase, and then we'll do main. That's it. See how it said, you might have noticed it was pretty quick. It said reapplying 1 out of 3, 2 out of 3, 3 out of 3. It reapplied the 3 commits. So now if we do git log, we've got that new one here. And it actually is considered before our other commits because we've moved our timeline, right? So the test 4, even though it happened after, we rebased on top of that commit. So we look at the parent. This is our most recent commit in new branch. The parent is ours, sure. Okay, let's look at this one. Before it was, and commit is, you can do the -p, it doesn't really make a difference. Commit, so this is the commit right after the main one. The parent is now test 4. Now I forgot to show the parent wasn't that before, but if before we rebase, the parent would have been edit some files of this commit right here. So cool, that makes sense. And we can actually see that these commit IDs changed. So when you rebase, it's recreating those commits. That's why you have to force push. You're changing history. So if you notice, the ID of edit some file, or sorry, the ID of add test1 file on new branch before we rebased was this ID, and then this one was this one, this one was this one. They're all, and then look down here, they're all different because they recreated them. So we can actually still look at this. It doesn't matter that we already rebased. We can still, this commit's not gone forever. We can still look at this. So if we copy it and we do git cat file, this is the commit before we rebase, the first commit on this new branch. Oop. Still there. And the parent is edit some files. So you don't actually, when something's committed, you don't lose it. Even if you've reset, rebase, whatever, you're not losing it. Unless you like delete .git, then you will lose it. But if you don't do that, you won't lose it. So cool. So we've got these 2 branches. Let's merge our new branch back into main. And this is something you're going to need to do. We're going to see that you probably won't do this from command line. 9 times out of 10, you're going to do it in GitHub on their web-based interface, which is fine. but we're going to show you what happens, how to do it manually. So if we're a new branch, we can say, okay, we've got nothing here. It's clean index. We want to merge those commits into main, which basically means, and we could rebase, but we're going to merge. We could rebase main onto this branch, but that would be a little weird because we're like rebasing branches that were based on each other now. It gets a little weird. So let's merge. So we say merge. We want to be in master, or main in this case, switch main, and then we do merge new branch. That's it. And now all those commits are here. Cool. And we used fast forward, which I think, let's just take a look here. Yeah, so there's only one parent. That's the way we did the merge. Typically, merges will create a merge commit that has an alt, like a two parents basically, and we'd be able to tell that it's a merge commit. Oh, something just opened on my computer. Sorry. We'd be able to tell that it's a merge commit because it's got two parents. So I'm just gonna really quickly grab something here. Okay, so I'm going to show the alternative if you did want to see the merge commit. Let's just do that. We'll create a new branch. Let's check our switch. You don't have to do this, but we'll create another branch really quick. Test branch 1, we'll say. We'll make a file, empty file. It's not actually empty. Now we've got, again, right? So if we go back into main, actually, let's do it into new branch. I'll show what it looks like. It doesn't have to be main. We can merge that in. So let's say git merge test branch 1, and let's say no fast forward. So see, it's opened this thing. Now, because we said no fast forward, we're introducing the merge commit. So if you do this in GitHub, you merge, and if you do pull, it will create a merge commit. But if you don't, if you just do git merge, the default is that it fast forwards. It doesn't do the merge commit, which I actually think the merge commit is useful because it shows at what point the branch is merged, which is really important if you're using the merging strategy. So, okay, we've got this file. We don't need to change the commit message. We'll just do write and quit. Now if we go back into, if we do git log, see how this fancy schmancy UI here shows us that we branched out and then we merged, and this is the merge commit. So if we look at this, we can just do git cat file, and this merge commit's only created in the branch that you merged into. So let's do cat file -p, and we'll look at the head. So now it's got two parents. That's a merge commit. Okay, so moving on. We're coming into the home stretch here. I know we're way over time. I kind of lost track of time, but hopefully this is still interesting. So yeah, if you have to go, feel free to go, and we can send out the recording. If you can't stay for any longer, that's all good. A lot of the bulk of this information is already been done. From this point on, we'll just be talking about how to work collaboratively with GitHub and all that. So you can totally do it on your own time. I can send out the recording, but I encourage you to stay if you can. So working with remotes. Remote repositories enable us to collaborate asynchronously. So remote repositories are hosted on some network, usually the internet, like GitHub hosts repositories. We'll see. Individual contributors, ICs, can clone the remote repository to their machine. So that's where this whole distributed version control system comes in. You are cloning, you're mirroring the remote repository on your computer. You have a full copy of it that mirrors the upstream. The remote is the single source of truth, but you have a full copy on your computer. Okay, so you pull changes down from the remote and you can push changes up to the remote. And a repository without a remote is just considered a local repository. So if you just do Git init, you don't have there's no GitHub involved. You're not pushing the repository anywhere. That's a local repository. That's all. Okay. So now with that, we can talk about GitHub. Where does GitHub play into it? What is GitHub? So GitHub is a Git repository hosting platform or service with a plethora of tools to facilitate collaborative software development. So there's all sorts of features in GitHub, issues, project boards, discussions, all sorts of crazy stuff. But the core feature of GitHub is that it allows you to host Git repositories publicly. You can work with others rather than, you could set up a Git server on your home. You could set up a Raspberry Pi and host a Git server and host a repository in there and it'd be the same effect. But I mean, GitHub's free, so why would you do that? And there's a great interface. So GitHub is not Git. It's not the same thing, but it is tightly tied. So GitHub repositories, there's two kind of models for working in a GitHub repository. There's the shared repository where all developers work in the same repo and have mostly the same permissions. And you must be an authorized contributor to be able to contribute to a shared repository. In most cases, pull requests are still part of the process for the code review part of it. And we'll see what that looks like in a sec here. We've only got a few more slides here, so we're almost done. Then there's the fork and pull model, this is if you have a public repository, but you don't introduce any contributors. I have a repository on my profile, and you want to open a pull request, but you're not a contributor. You can fork my repository, which means cloning it under your own account, as long as you have permissions to read it, like it's a public repository or I've given you explicit permission in settings. You can make changes on your own fork. You can do whatever you want with the fork. It's your own repo. And then you can open a pull request to merge your branch on your fork into my repository. So that's a different model. Typically, any project you're working on in Vike Labs, you're going to be a shared repository. So fork and pull would just be something if you're working on an open source project maybe, and you wanted to introduce some changes. Typically, you'd probably fork it and make a pull request that way. So GitHub has its own flow. What does that flow look like? Well, first you create a branch in your project where you can experiment, make changes. This is why it's important to branch off. It doesn't affect main. You can always delete the branch, do whatever you want. And then you add your commits, and then you open a pull request. And we're going to talk about what a pull request is on the next and I think final slide. So we're in the home stretch here. Pull requests are basically requests to merge. And GitHub allows you to have this interface that you can do code review. You can comment on the code, you can get feedback, you can so you discuss and review here and you make changes. And then eventually when it's ready, you merge and deploy. Now, throughout this process, main might change. And at that point, you might want to rebase your branch onto main. And then you're going to have to force push. I think this is okay. This is the model that I would encourage my teammates to use in Degree Planner, but your team lead might have a different strategy. They might prefer merges always, but I prefer if it's in a pull request and you need to update your branch from main, I prefer it. Like my model is I rebase onto the tip of main and then I force push. And it's okay because that branch is just in a PR. It's not like everybody's working on this branch. Force pushing is bad when it's a branch that multiple people work on. Don't do it. If it's something multiple people are working on, don't force push. Now, you can also merge as well. That's another strategy we talked about. But at the end, we've got our branch and we can merge and deploy it into the main thing once the pull request has been approved. And when at that point, there's a few strategies you'll find. When the big green merge button appears in your pull request, there's also a drop down where you can select if you want to squash your commits, you want to merge it, you want to rebase, whatever you want to do. That's just different strategies to merge it in. I won't get into that. We don't have time. But in general, you can, at this point, you can also edit, you can go back and I would personally rebase, do an interactive rebase before I merge into main, and I would clean up the commits. Because interactive rebasing, I'm not going to get into it. I'll send out a resource that teaches you how to do that and what all the commands do. But you can drop commits. You can squash them into one. Like if you have 2 commits, like say you add something and then you immediately remove it, you might as well have 1 commit, right? You might as well drop them completely. If it adds something and then removes it, you might as well just drop those 2 commits, and you can do that. So that's the strategy. So what is a pull request? A pull request is a request to merge one branch into another. It's almost always used for code review purposes. What makes a good pull request? This is really important if you're collaborating with others. A good pull request is small and digestible. The commits are well organized. All work is logically connected. And the pull request message describes what the PR does and provides any necessary background. So they need to be small. That's the biggest thing. Pull requests should be small. If there's more than like 8 files changed, it's going to be hard to review. If there's more than, 500 lines, that's going to take a while to review. So you want to keep them small. You can always open PRs, and you can base PRs on other PRs if they're dependent on each other. That's another thing. They should be descriptive, and all the commits should be good. Commit messages should be very descriptive, and they should have one specific thing happening in the commit. It should have a good heading, and it should have a good body. Why is the change necessary? How does it address the issue? What side effects does it have? All these things should be included in a commit message. So this is our last exercise before we finish. If you already know how to use GitHub, you can drop off at this point. There's no new information that I'm going to provide. This is I'm going to show you how to basically create a repository in GitHub, clone it. And sorry, I forgot to change this slide. We're not actually going to clone this specific repository. We're going to do a different one because I would have to add you all as contributors. So I'm just going to show you in my window here. So if you go to github.com/new, you're logged in. You can create a new repository, or we'll call it Git Workshop. People are dropping like flies. Okay, so we create this repository, and if you skip this step, let's say we don't want to create a whole new one. Let's try and push what we did throughout this whole workshop. Let's push that all into a repository. We've already done the initialization on our end locally. We want to push it to GitHub. So skip all this. Cool. So this tells you exactly how to do it. You do git remote add. Now, if you do git remote, you can see all the remotes. It's just origin. That's the only one we've added. Origin is the default for like the remote. So now if we do git branch main, now we've set that branch as the main branch, and we can push. And -u just means set the upstream to origin. So we're basically saying make the main branch, push that, and make that public on our GitHub. Cool. Now let's refresh the page. Look at all these cool files we have. Awesome. We can see the commits. Pretty cool. Okay. So now we didn't push any of our other branches. We can do that separately. We would have to do it like this. If we're in a different branch, switch test branch 1, I think it was. Yeah, we can do this. Now, if we refresh the page, nothing changes about main, but we have a new branch. Now we can view it here. Now, what if I want to create a pull request? So I've just pushed this branch. Maybe I've made some changes in test branch 1 that I want to merge into main. That's when I create a pull request. So and it gives you, it's super handy. It gives you a link. You can also just go to the repository and it'll tell you, usually, in this case it didn't, but usually it tells you, I might have to be on this branch. Okay, so yeah, if you go onto the branch, it tells you pull request. We're actually behind main, which is interesting. But let's say we want to do a pull request to merge this branch in. Or we'll do a new one because this one's behind and I don't want to deal with that. So let's do a new one. New branch to merge. No, I'll just call it new branch. Okay, we'll do one commit. You can also do git commit -a, and that'll add everything in your working directory to staging and then commit it. So you don't have to do git add. Oh, sorry, I forgot to do the message. And then you do add test. Wait a minute. Thought it was dash. Okay, well, I think I did the commit wrong, but we'll do it this way. Okay, we've added this file. Let's push our branch, and it'll tell us we need to set the upstream, so we can do it with -u, origin, new branch. Awesome. Now, we can see this is the prompt I was talking about. It'll tell you new branch was just published. We can do compare and pull request, or we can do the link that it provides. This is where we do our pull request, so we can say add test file to demonstrate how to open a pull request. And in this, you might have, a template, maybe your team lead or whatever project you're working on, there's a template for your pull request. In this body, you would want to talk about what the PR does, the dependencies, background information, all that stuff. We're going to leave it blank because it doesn't really matter in this case, at least. So we do create pull request. And GitHub will run some checks if we've configured. We can run CI checks, testing, things like that, and it'll tell us if we can merge it. Now, we don't have anybody else contributing to this repository. I haven't set up any sort of access control. Normally, it wouldn't allow you to merge until someone approves it. At this point, someone could come in and go files changed or commits, and they could look at it and say, okay, I'm going to add a comment here and say, change this to blah. We can start a review. Normally, I would not be the person reviewing my own code, but we can do that. We can say finish the review. We can request changes. Can't do that because I'm the author. But let's say I did do that. It would show me that someone had commented and that I need to change it. So then I change it, and then they go back and they approve it, and then I can merge it. And I press merge, confirm merge. Now at this point, I was talking about you can squash and merge, rebase and merge. Create a merge commit. If you merge this one, if you just do the default, you will merge your PR with every commit you made in your branch will go into main, will be visible in main, which can be kind of messy if you have a lot of commits in your PR. You can also do squash and merge, which squashes all of your commits into one commit. You can also do rebase and merge, which is, again, it's rebasing. So in this case, it wouldn't really matter because we only have one commit, so we'll just do merge. But you do merge. Cool, and then you can delete the branch. So now, if we go into main, we've got another commit, plus, so we've got the commit we made in our branch, plus we've got merge pull request 1. Awesome. So you can also pull from the changes. If we make a change, somebody makes a change to master, we can do git pull, and that will pull down any changes. So what this is saying is it's saying, hey, I tried to pull this new branch, but it's deleted from the remote, which is as expected. So we shouldn't really be using it anyways. We could delete it, but let's say main, maybe some changes. Cool. We merged those two, the commit we made in the other branch, and we also have the merge commit. So now we can do git pull, and it'll make our local repository match what's in the remote. And with that, I will conclude the workshop that went half an hour over time. I apologize. Pretty much everyone's dropped off at this point, so I'll definitely send out a recording. I appreciate everyone who stuck around. I didn't intend on being this long-winded, but I didn't really have a chance to fully rehearse it. So that's it. Hopefully that helps. I'm going to be sending out some resources to help you further and some exercises you can do if you want. There's tons of resources online, but hopefully that sums it up. My goal with this workshop was basically to avoid this. So this is one of my favorite comics from XKCD. It says, this is Git. It tracks collaborative work on projects through a beautiful distributed graph theory tree model. Cool, how do we use it? No idea, just memorize these commands and type them to sync up. If you get errors, save your work elsewhere, delete the project, and download a fresh copy. So that's kind of the joke here. Disaster recovery in Git, just remove the repository and restart. You can always do that, but you're losing all your commits and stuff that aren't pushed to master or the remote. But yeah, the idea, and if it doesn't fix it, you can you can call your friend and they can explain it to you. So that's it. I'll send out some resources to help further, but that concludes the workshop, and here's some references, and hopefully that helped everybody. And I'll be sharing this presentation as well as the recording and the resources, maybe this weekend or tomorrow if I have time. Thanks, everybody.